Good day. My name is Ryan Cumings, and my advisor is Dr. Saleh Faruque from the University of North Dakota Electrical Engineering Department. Today, I will be presenting the laser communication relay. The tasks for this project include developing an optical receiver. This module utilizes photodiodes and a differential configuration. Optical transmitter. This module utilizes a laser diode operating in the near-infrared spectrum. Signal demodulation and modulation. For analog signals, this includes amplitude modulation and frequency modulation. And for digital signals, amplitude shift keying, frequency shift keying, and phase shift keying. High speed and analog integrity are a design consideration during the layout and routing process. 50 ohm interconnections are utilized to interface in lab equipment, as well as provide loopback capability to allow relay functionality. 3.5 mm tip ring sleeved sockets are utilized to interface with audio equipment such as headphones or iPods. The processing section will utilize signal regeneration for FM, amplitude shift keying, frequency shift keying, and phase shift keying. Automatic gain control circuit is required to regenerate AM signals. High power, high speed devices are utilized for this project. The purpose of utilizing these devices is to allow for exploration of the capability of the system without running into device performance issues. Lower speed devices may be utilized based on performance requirements of the application. A microcontroller is supplied on board to provide multiplexing capability for the transmitter as well as the audio output. The microcontroller has the ability to modulate and demodulate FM and binary phase shift keying in software. The receiver is set up as a differential photodetector. The selected photodiodes have a peak in the sensitivity at 850 nanometers. Photodiodes are biased to improve sensitivity and frequency response. The photodiodes shown in this arrangement allow for both the ambient light current and dark current to cancel. The signal current will result in an imbalance of the current. The result is sent to the transimpedance amplifier. The output of the transimpedance amplifier is sent to the gain stage. As a note, the feedback resistor U7RF was changed to 33 kiloohms in the final product. The low impedance bias makes use of Zener diodes. Shown here is the positive bias with the negative bias similarly configured. The methodology is to provide a constant current source that is adjustable for testing and able to reject variations in power supply voltage. On the right is a current sink that provides biasing for the Zener diode DZ3 clamped to the positive rail. A potentiometer allows adjustment of the voltage desired across the current sensing resistor, RZ1. Both the set point and the current sensing resistor voltages are fed into the differential amplifier. This allows a constant current nearly independent of supply voltage sent to the photodiode bias Zener DZ1. The selected operating point has a Zener impedance of 4 ohms. As a final note, in the final design, RZ11 was changed to a 1.1 kiloohm resistor to raise the bias current of the differential amplifier. The transmitter laser diode transmit at 850 nanometers. This is a relatively quiet place in the optical spectrum that allows for the signal to be differentiated from background with greater ease. High-speed op-amp unfortunately does not have the required voltage range to drive the laser diode directly, and sense the current as well. This forced the requirement to utilize a transistor to drive the laser diode. The BJT was chosen specifically because it is a current-controlled current device. MOSFETs have additional capacitance which reduce the speed and raises ringing. The current source is enabled by having the current jumper installed as well as having the microcontroller turn on transistor QE5. A 300 MHz op-amp is currently being utilized to force compliance of the laser diode to the command signal. A strengths command is desired to allow compatibility with different components. 1 volt is full scale, 0 volts is only the bias current. Differential input reduces common mode interference. The laser diode chosen has capabilities of a Class 3 Bravo laser. Safety is required as injury may occur with no warning. The benefit of the current buffer concept is that the maximum power is limited to 3 milliwatts, with a nominal average power of 1.5 milliwatts. Reclassification of a laser class cannot be performed without actually measuring the output power. However, OSHA allows us to calculate safe handling practices. The 10-second limit is applicable for infrared devices due to the natural movements of the eye. The 8-hour limit is based on continuous exposure during an 8-hour workday. The laser diode chosen has capabilities of a Class 3 Bravo laser. Safety is required as injury may occur with no warning. The benefit of the current buffer concept is that the maximum power is limited to 3 milliwatts, with a nominal average power of 1.5 milliwatts. Reclassification of a laser class cannot be performed without actually measuring the output power. However, OSHA allows us to calculate safe handling practices. The 10-second limit is applicable for infrared devices due to the natural movements of the eye. The 8-hour limit is based on continuous exposure during an 8-hour workday. The use of solid cone angles allows rapid calculation of different radiant intensities based on distance. To determine the 8-hour OSHA limit, the radiant intensity of the laser is divided by the OSHA limit. The root of the result gives the maximum hazard distance. The user is safe as long as they do not view the direct beam between the transmitter board and the receiver board. Laser safety is additionally accomplished by the use of jumpers and an RS-232 serial interface. The emitter can be physically disabled by creating an air gap through the current source or shorting the laser diode. Remote functionality is also enabled by the use of the RS-232 connector in the microcontroller. The alignment procedure enables the user to select the maximum current, the full-scale current, and the bias current. The use of the shorting jumper for the laser diode enables the user to adjust the potentiometers without risking injury. The alignment verification of the laser diode allows the user to be assured that the laser can be handled safely as described in the laser safety section. Additionally, when transmitting analog baseband signals, this ensures the linearity between the commanded strength and the emitter power. The yellow trace is the current output from the laser diode. Note the sharp edge on the square wave. The blue trace is the selected output of the receiver. In this case, the result is the direct output of the receiver. For AM demodulation, a simple envelope detector is utilized. The circuit only rectifies the positive peaks of the signal. This circuit can detect both negative and positive going photodiode. The AM carrier signal is set to 1 MHz. This results in a clean demodulated signal. Notice the distortion on the negative half cycle of the output sine wave. The envelope detector also results in distortion of the square wave due to the high pass filter on the audio output. Pulse width modulation has also proved to be an effective method of transmitting signals. By sending the pulse width modulated signal to the same envelope detector as the AM signal, we are able to recover the original audio. The pulse train frequency is set to 5 MHz with a duty cycle of 50%. The deviation is set to 25%, which results in the cleanest sounding signal. As you can see, there is much distortion for both signals. Frequency demodulation requires a frequency to voltage conversion. A phase lock loop is one solution to this problem. The receiver output is fed into a phase frequency detector. This circuit creates an error signal, which is fed into a low-pass filter. The voltage-controlled oscillator has a nearly linear voltage to frequency transfer function. Due to the high gain of the phase frequency detector, the phase lock loop will lock on to the receiver's frequency. The output from the low-pass filter is buffered for use to minimize loading of the phase frequency detector. The range of the frequency lock and offset determines the frequency to voltage transfer function. A smaller lock range equates to larger voltage changes for smaller frequency deviations. This comes with a price, as jitter of the source oscillators as well as the receiver oscillator directly equates to noise. A loopback function is utilized to test the transmission of digital signals. The user connects to a serial port utilizing a terminal program. The transmission line of the RS-232 is coupled to the laser transmitter to transmit the information. As the information is received, it is then limited back to TTL levels and then fed back to the terminal program. We can see examples of the transmitted capital E in two types of transmission scenarios. On the left is on-off keying, and the right is frequency shift keying. The on-off keying method was found to be more reliable than the frequency shift keying with regards to signal recovery. The phase frequency detector has a minimum and maximum voltage that it will output. This minimum voltage is right on the threshold of the low voltage of the RS-232 receiver. The data rate for the binary phase shift keying was 33 kilobits per second, with one synchronizer bit included for every 5 data bits. At 5 data bits per sample, this results in a sampling frequency of 6.67 kHz. The algorithm utilizes 8 synchronizer bits. This is not a performance algorithm, but it is robust and can synchronize mid-data stream. 5 microseconds of jitter margin are shown at the selected data rate. Differential encoding results in a 1-bit delay. However, this allows for phase inversion when aligned to either the positive or negative detector. Audio data was able to be transmitted utilizing the onboard microcontroller. Korsakov's Flight of the Bumblebee is utilized to sample audio. The original is played here for comparison. The laser communication relay has the ability to transmit and receive unmodulated or baseband audio data. The frequency modulation is performed in software with amplitude proportional to period plus an offset. 167 kHz is the lower frequency, and 500 kHz is the higher frequency. These were chosen to reduce processing complexity as the periods for these frequencies were multiples of the clock speed. The binary phase shift keying mode is also able to transmit audio data. At 3.33 kHz, aliasing occurs due to the low sampling rate. Projects performed in other courses led to completion of source and error coding prior to completion of phase shift keying demodulation, which remains the only outstanding item that was not completed during the fall semester. The spring semester task included completion of signal decoding, design of a solar power supply, circuit design, manufacture, assembly, and testing. The high power requirements for the testing resulted in a solar power supply becoming prohibitive. In closing, the transmitter module is able to send analog data at rates exceeding 10 MHz. The receiver module is able to amplify signals to create a consistent 2 volts peak-to-peak signal with a 1 volt DC component. Data is able to be modulated and demodulated using AM, FM, amplitude shift keying, frequency shift keying, and phase shift keying method. Future work includes investigating lower power designs and low noise amplifiers. Thank you for your time.